Hello to everyone. I'm Professor Giuseppe Ciaburro from the School of Engineering and Informatics at Pegaso University. My research focuses on sustainable materials and innovative approach for noise control and acoustics. Today I'm excited to present our latest work titled Sound Absorption Performance of a Layered Recycled Metamaterial with Machine Learning-Based Acoustic Simulation. This study combined experimental characterization of recycled layered composite with data-driven modeling using machine learning to predict their acoustic performance. Our approach aims to provide sustainable, high-performance solution for building acoustics and noise mitigation, highlighting the synergy between material innovation and advanced computational methods. The development of sustainable material for noise application is becoming increasingly relevant in the context of environmental protection and circular economy strategies. In this study, we present a new layered acoustic metamaterials made entirely from recycled components, specifically cellular polypropylene membranes combined with a honeycomb structure of aramaic paper. The material was manufactured in configuration of varying thicknesses, reaching for up to 3 layers, in order to explore the influence of layered and structural complexity on its acoustic performance. The acoustic properties were characterized experimentally using a Kund tube, focusing on the sound absorption coefficient across a wide frequency range. The results demonstrate that the proposed layered material exhibits significant absorption capabilities, particularly at low to mid frequencies with performance comparable to conventional porous absorber. The metamaterial was constructed by combining 2 mm recycled cellular polypropylene membrane with a 13 mm aramaic paper honeycomb core. To study the effect of thickness and structural complexity, 3 configurations were produced. The first consisted of 1 membrane and 1 honeycomb layer. The second included 2 membrane and 2 honeycomb layers, increasing internal interaction. The final configuration, the one shown in this slide, used 3 membrane and 3 honeycomb layers, forming the thickest and most complex structure. This progressive layer allowed us to investigate how to adapt depth, interface, and resonant cavities influence the overall sound absorption performance. The acoustics performance of the material was evaluated using a standardized Kund tube, focusing on the sound absorption coefficient over a wide frequency range. Measurements were carried out with a cylindrical impedance tube featuring a 100 mm internal diameter and 560 mm length, suitable for level testing up to 2000 Hz. 2 1/4-inch precision microphones spaced 15 mm apart captured pressure variation in the sound field, ensuring accurate results above 200 Hz. This setup enabled a detailed broad-spectrum characterization of how each layered configuration absorbs and dissipates sound energy. We adapt a machine learning simulation model to extend the experimental result. This model is capable of predicting the sound absorption coefficient of the layered metamaterial. A supervised artificial neural network was trained using the measurement made on sound absorption coefficient data as ground truth, enabling the model to learn the frequency-dependent behavior of each configuration. Once trained, the ANN could rapidly simulate the acoustic performance of new layered structure without physical testing. This data-driven approach allowed efficient comparison between specimens and provided a fast tool for exploring design variation, supporting the development of optimized and sustainable acoustic materials. The sound absorption coefficient measurement show that the layered recycled metamaterial achieve strong sound absorption, especially in the low to mid frequency range, where many building acoustic applications require improved performance. Across all the configurations, the absorption levels were comparable to conventional porous materials, confirming the effectiveness of the recycled component. The aramid conical structure played a key role in enhancing performance by introducing multiple scattering paths, internal reflection, and resonance effect with the cavities. Thicker multi-layer configuration further increase absorption bandwidth, demonstrate how structural complexity positively influences the system overall acoustic behavior. The artificial neural network model for sound absorption coefficient prediction was trained using three input features: frequency, number of membrane layers, and number of honeycomb layers. Frequency were considered in 1/3 octave band from 2050 to 2500 Hz. The model output was the predicted SAC value for each band, corresponding to the specific thickness. Because the output is numerical and continuous, the task was formulated as a regression problem with two structural predictors and one acoustic response variable. The artificial neural network was trained using experimental data, enabling the network to learn the relationship between layering, frequency, and absorption performance with high accuracy. The artificial neural network model was trained on 288 samples, divided in 70% training, 15% validation, and 15% for testing. Model performance was assessed using mean square error and the correlation coefficient. The training network achieved a mean square error value between 0.0085 and 0.0119, indicating low prediction error across all sets. The correlation coefficient ranging from 0.9273 to 0.9432 show a strong correlation between predicted and measured SAC values. This result confirmed that artificial neural network model accurately captured the relationship between frequency, layering, and acoustic behavior, providing a reliable tool for predicting the performance of a new metamaterial configuration. This study demonstrates the strong potential of recycled layer composite for sound absorption in building acoustics and noise control. Experimental measurement confirmed that multi-layer configuration with polypropylene membrane and aramidic honeycomb achieve effective low to mid-frequency absorption. Complementing this, a machine learning model successfully predicted the acoustic performance of the new configuration, reducing the need for extensive testing. The combination data-driven modeling experimental validation provide a provable framework for designing sustainable acoustic materials efficiently. Overall, this approach highlights a promising pathway toward environmental-friendly, high-performance metamaterial for future noise mitigation applications. Thank you for your attention.